Martin, you can start sharing your slides.
All right. Can you hear me? Can you see this?
That looks great. Thank you.
Perfect.
All right. It's going to be our last session for the conference. I'd like to thank all of our speakers and also the ones that are sticking it out for the very last session. I applaud you. And I'd like to thank everybody on behalf of the SOC for coming either in person or remotely. It's been a real pleasure to meet many of you and talk with you for the first time. So might as well get started on this last session. Supernova remnants of all types, and then Brian Williams will enlighten us. I'll start with our first talk. Martin Mayer from MPE. He will be talking about Puppis A and how it looks with Ejecta. So this is a 15-minute talk, Martin, and you are free to begin.
All right. Thank you very much. And good evening from Germany. Yeah, thanks for this opportunity to present my work here. My name is Martin Meyer. I'm a PhD student from MPE in Garching. And today I would like to present to you one of the first spatially resolved spectral analysis of a supernova remnant that was carried out with Ejecta. And since we're in the session which gives a look to the future, I thought I'd introduce Ejecta at least for a little bit, even though many of you might be familiar with it. It is the soft X-ray telescope aboard the SRG mission, which is a German-Russian collaboration. And the original mission goal is to carry out a 4-year all-sky X-ray survey, which even at this point is already many, many times deeper than the precursor all-sky survey from ROSAT. On the right, I'm showing an image from Ejecta while it was still in the lab. And you can see that there are 7 identical telescope modules, or TMs, and each of these modules has a single chip CCD detector, which is sensitive to X-rays in the broad range of 0.2 to around 10 keV. And what makes Ejecta unique is the combination of a 1-degree field of view and a quite large effective area. And in combination, this makes the instrument the currently best X-ray survey mission, which is illustrated here on the right, where the product of the field of view and the effective area for different X-ray instruments is plotted. And you can see in this region around 1 keV, Ejecta is many times more sensitive than previous X-ray missions. But a further important point is that it also has an improved spectral resolution compared to previous CCDs based on this similar technology, such as EPIC-PN, which is shown here in this comparison of 2 spectra of 1987A. And you can see clearly that spectral lines are resolved a lot better with Ejecta, and also the low energy redistribution of events is strongly suppressed. The target of the analysis I would like to present is Puppis A. Many of you will be familiar with it. It is a very X-ray bright, around 4,000-year-old core collapse supernova remnant. We know it's a core collapse because we see a neutron star at its center. And it is, if you look at the size, it is sort of the ideal target for Erisita because it measures around 1 degree in diameter. It is known to be an oxygen-rich supernova remnant based on optical spectroscopy. And we also know that here along this eastern rim, there's intense interaction with dense interstellar medium, explaining this high X-ray brightness. A further thing which is going to become important is that the neutron star in this supernova remnant actually has a very precisely measured trajectory, and it's moving towards this southwestern direction at around 500 kilometers per second. The Erisita dataset, which this image on the right is based on, is from an around 30 kilosecond long observation, which was carried out before the start of the All-Sky survey as a PV observation. And the target of our analysis was to investigate sort of the global distribution of parameters, such as temperature or also elemental abundances across this entire supernova remnant. Before I get into the analysis details, I would just like to present you a very quick look at the data. What I'm showing here is a very simple integrated spectrum, just collapsing the event list over the entire remnant, and you see a lot of very well-resolved lines. And what we can do with this, rather than fit it, is divide it into many narrow energy bands, and then in each energy band extract an image. And this is shown here on the right. What you see here is an animation that loops through this data cube of images from low to high energies. And if you keep looking at it, you will notice that we see quite strong differences between the energy bands. In particular, if you look here at this southwestern part, you see this is very strongly absorbed at the lowest energies. Furthermore, if we focus on this part at the northeastern rim, where I already said there is some interaction with ISM ongoing, you see it becomes more and more dominant as we go to highest energies, indicating a high temperature. Furthermore, if we focus on individual energy bands, we see there are these clumps which seem to pop out and pop back down between energy bands, and that might be a signature of emission lines from Ejecta. Now, in order to quantify this, we performed a spatially resolved spectroscopy. And to do that, we divided this remnant into around 700 independent spectral regions using Voronoi binning. And from each of these regions, one spectrum was extracted with around 40,000 X-ray photons in it. And I'm showing here one representative spectrum, and you can see even there are still quite many lines resolved down to this silicon 13 line at around 1.8 keV. And we modeled each spectrum with a relatively simplistic model of a plane parallel shock plasma under non-equilibrium ionization conditions. And then by combining the results of these fits for each region, we were able to create parameter maps spanning the extent of the entire remnant. And that is what is shown here now in the two left panels. On the left, I show the distribution of absorption column density towards Kapis A. And you see quite clearly on large scales, this southwestern part stands out, very much consistent with the fact that there's seems to be high absorption also directly in imaging, as we see mostly the hard band, which is shown here in blue, seems to be dominant. If we compare this also to the temperature of the plasma, which was measured, we see on large scales again, we see a two relatively interesting tendencies. For one, we confirm that this region at the northeast rim really has the highest temperatures in Kapis A, around 0.75 keV. However, in contrast, if we look at this eastern circular structure, we find that it has extremely low temperatures. So that is a quite interesting sign that something different seems to be going on in this region than in the other regions. Moving on, let's try to characterize when in each region the material was struck by a shock wave. And to do this, we use two parameters returned by our fit. One is the emission measure, which quantifies the normalization of the spectrum, and one is the ionization age, which quantifies the departure from perfect collisional ionization equilibrium. And by solving the normalization for the electron density, assuming a very simplistic volume, we can infer approximately when in time material in each region was struck by a shock. So implying how recently the shock wave passed through individual regions. And we can see quite clearly a few regions stand out here in dark, meaning they have a low shock age, meaning they have been recently struck by a shock wave. And if we overlay this with the actual image that I've shown you before, we see that especially this filament and this clump correspond to features which are also standing out directly in imaging as relatively soft structures. Furthermore, if we look at this knot here at the eastern rim, we can observe quite nicely how this shock age it starts out at a relatively high value, meaning it has been shocked a long time ago. But then as we approach the outermost rim of the shock wave or the forward shock, this shock age decreases, consistent with the fact that material right behind the forward shock was heated only very recently. Finally, let's try to search for some supernova ejecta in this remnant in consistency with what we have been doing so far in this conference. What I'm showing here is the elemental abundances normalized to the solar value for 6 typical ejecta elements across the entire remnant. And without going into any detail, I would just like to emphasize that this region, which I've highlighted in elliptically here, seems to exhibit the peak in elemental abundance in oxygen, neon, magnesium, silicon, and sulfur. So there seems to be a high concentration of ejecta there, whereas in the entire rest of the remnant, we do not see any similar clumps. Furthermore, if we look at this iron abundance, note that the maximum of this color scale is only at solar abundances. It is kind of unclear if we actually do see a peak there too, or if this is maybe just a systematic in our fit. So overall, I would refrain from claiming that we have actually detected iron ejecta in our fitting. Now let's try to go a little bit deeper and get some physical implications out of this. The first thing is related to what we heard today in the first talk, actually. It is that we can actually correlate the direction in which the neutron star is moving and the direction in which heavy elements or intermediate mass elements, such as silicon, are located in the remnant. And they're expected to be anti-correlated in a hydrodynamic neutron star kick scenario. And if we try to perform this exercise, we see that the location where these silicon ejecta seem to be located does not quite perfectly correspond to the anti-center, so to speak, of the neutron star motion, but it deviates by around 55 degrees, which begs the question, is this an intrinsic observation? Is this maybe something that the models cannot predict more precisely? Or is this maybe also due to the bias that we have in our X-ray view of the ejecta? Because in X-rays, we can only see ejecta that have been heated relatively recently by the reverse shock, meaning if ejecta have cooled down or clumps have been destroyed or they are just not shocked yet, we would not see them here. Furthermore, let's try to do some basic physics with the apparent composition of ejecta. Simply from comparing the oxygen and the silicon abundances, we see that silicon seems to, for some reason, be much more prominent, both in extent, but also in the maximum abundances. This becomes even more clear if we divide these two maps by each other, and we see this extended region where we find almost 3 times the solar silicon to oxygen ratio. If we try to integrate over all ejecta clumps and estimate a mass ratio of silicon to oxygen, we get values between around 0.4 and 0.7, depending on the exact approach. And I'm no expert on nucleosynthesis of CCSNRs, but my impression is that this is unusually high for if it is seen as the integrated yield of this core-colored supernova. So again, this is the question I want to ask. Is this because something is wrong in these nucleosynthesis models? Or is it just because the X-ray emission of ejecta is not representative of the true composition? Because, for instance, a higher fraction of silicon ejecta might be visible in X-rays at this time. This brings me already to my conclusions. I hope to have shown you the potential of this deep Rosita observation in the spatially resolved analysis of a supernova remnant, such as PAPIS-A. The key findings we had were that there are very large-scale gradients, both in the foreground absorption, but also in the temperature of the plasma in this remnant. And together they create this sort of blue stripe, which seems to cross this remnant. Furthermore, we have found several regions in which the material seems to have been struck by a shock wave very recently, either a forward shock if we are close to the rim of the SNR, or maybe also a reverse shock if this is if we're talking about ejecta clumps. And finally, we have looked for ejecta through the entire remnant, but we have only found signatures of them in this northeastern part of it, and the rest of it seemed to be more or less devoid of ejecta. And naively, at least, if we compare both the location and the composition of our ejecta with what we would expect in the simplest theoretical scenario, these seem to be somewhat in conflict with it, but there are biases which we should not forget about. And if I have managed to spark your interest with this, I would like to refer you to this paper published this year, in which all of this is explained in much more detail. And now I hope that you have some questions for me. Thank you very much.
Do we have any questions? Okay, I have a question. So you say that probably all of the X-ray emissions coming from swept up circumstellar material, is that what you're sort of suggesting? Except
No.
for a part that is ejecta?
Yes, I mean, we know it's a relatively medium, like it's not as young as Tycho or other remnants we have seen in, or Cas-A we have seen in this conference. So we expect a very large percentage of circumstellar material. And if we can detect ejecta, or at least my guess would be it should be in sort of clumpy structures as we've seen here.
I guess my question is, have you made a crude estimate of the swept up mass?
Mm-hmm. Yes. Actually, I might have a slide on this. Yes. So we can very simply, by the normalization of the spectrum in each region, try to infer a density electron or proton density in each region by assuming a simple distance along the line of sight that is covered by the material, and also assuming a volume filling factor. And then if we convert this density in each region to an integrated mass, I get this estimate of around 80 solar masses, which however scales strongly with the distance to the remnant, because size of each region scales cubically to the distance. But yeah, what I've done and what I didn't have time to go into, unfortunately, was to compute this mass. And if we go a step further and try to convert this into a pre-explosion ISM density, we get around 10 to the minus 24. And if we go even further and use a simplistic set of Taylor model to convert this to an explosion energy, we get a value on the order of 10 to the 51 erg. So it seems to be more or less consistent with what you would expect. But of course, it's not very detailed modeling.
Okay. I see that Jiang He has a question.
Okay. Can you estimate absolute mass of ejecta, silicon or oxygen?
I tried, to be honest, but the masses don't seem to add up to what you would expect. In any case, I get below 1 solar mass. So we can be pretty sure that what we're seeing is not, sorry, 1 solar mass total ejecta mass, not individual elements, just to make that clear. In any case, we can be pretty sure that what we're seeing is not the complete ejecta mass for reasons that, yeah, maybe someone in the audience has a better idea on.
I think it's not bad because the rest of ejecta must have been, mixed with the ISM material, so you cannot separate from them, so kind of integrated. So it sounds reasonable estimate.
Yeah, maybe to add on this, if you just look at this, I'm sorry for zooming out in again, at this clump, which I've shown you, that was rich in silicon, and you try to basically approximate it as some ellipsoid in 3 dimensions, you get on the order of a total mass of this clump of 0.3 solar masses or something like that. So it is probably lower than the total mass, but it is, a fraction of a solar mass.
Good.
Let's thank our speaker again, and also
Thank you very much.
exciting to start to see some results from Ejecta on remnants that we're familiar with.
Paul, you can start sharing.
And next, I'd like to introduce Paul Pachinski, who's from here. And he will be talking about Chandra legacy observations in N132b. Paul, this is a 5-minute lightning talk.
You're muted if you're speaking.
There we go. Yeah, I got to get back there and get unmuted. Great. Thank you very much. Let's see. All right. Oops, hold on here. All right. Okay. Does that look good? Do
We see nothing.
you see it now?
We know, we don't see anything. You can try to share again.
Whoops. Sorry. Sorry about that. Okay, should look better now.
Yeah.
Are you full screen? Okay,
good.
very good. Well, I'd like to tell you about the work we've done to measure the expansion of the forward shock in the LMC Supernova Remnant N132D with Chandra. I want to acknowledge the wonderful team of collaborators we have working with us on this project. And I'd like to point out that Ji Long in particular, who has done most of the work for this project. So first, a quick introduction to N132D. It is the most luminous supernova remnant in X-rays in the local group. The image in the upper left shows you the beautiful Chandra image. N130D has a complicated elliptical morphology in X-rays with a relatively smooth shell in the south and a fragmented structure in the north. We estimated a progenitor mass of about 15 solar masses based on the Chandra data. The three-dimensional structure of the oxygen ejecta in the optical was shown to be toroidal in structure by Law et al. If you've not seen this paper, I strongly encourage you to take a look at it. It's a beautiful result. Law et al. Estimate an age of 2,450 years. And Banovitz et al. Have a new analysis where they estimate an age of 2,771 years based on an expansion analysis of the HST data. So we have a pretty good handle on the age of this remnant. N132D is also extremely bright in gamma rays. It's about an order of magnitude more luminous than Cas-A. And Jaco published the TeV detection last year. The two images in the bottom left show you the CO and H1 environment around N132D from Hidetoshi Sano's paper. There is a molecular cloud complex to the south of the remnant, and then the remnant occupies a cavity in the H1. And back in 1987, Jack Hughes suggested that N132D was a cavity explosion, so he was right on the money there, and Chen presented some of the detailed models for this case. So we've used two epochs of Chandra observations in 2006 and 2019, 2020 to measure the expansion of the forward shock over this 14.5-year baseline. We have a total of 17 observations been registered with respect to each other using a technique similar to what G showed earlier today for G292. This is a challenging and somewhat heroic analysis as it pushes the angular resolution of Chandra to its limits. The image in the lower left shows the 9 regions that we measured expansion for. Regions 1 through 8 are distributed around the southern rim, and region 9 is a special region up there in the northeast. The plot in the lower right shows you the expansion results for these 9 regions. We derive an expansion to about 110 milliarc seconds for the south rim and a little over 200 milliarc seconds for the northeast rim. And these correspond to shock velocities about 1,850 to 3,500 kilometers per second. So again, that region in the northeast has a much higher expansion velocity than the ones in the south rim. And you can see how the points are distributed in expansion for the regions around the south rim. You might want to say maybe there's some weak evidence there for an azimuthal variation, but given the uncertainties, it's not significant. So we've adopted that average value there, which is shown by the solid blue line, is what is the expansion of the south rim. We can also fit the spectra from these regions on the south rim. With a VP shock model, we allowed the abundances of oxygen, neon, magnesium, silicon, sulfur, and iron to be free. We get acceptable fits with this single component model, and the fitted abundances are consistent with the LMC ISM abundances, confirming that these regions are mostly swept up by ISM with little or no ejecta emission. The fitted temperature is about 1 keV, which implies a shock velocity about 855 kilometers per second, which is considerably smaller than our measured value of 1,650. And so this indicates that the ion electrons are not equilibrated just behind the forward shock. And then finally, comparing to some evolutionary models, we modeled the evolution using the 1D models in Truelove and McKee and expanded by Martin and others. We adopted our measured radii for the south and the northeast rims and the center of expansion from Banovitz. We assume an ejective mass of 2 solar masses. Then we can adjust the explosion energy and the ambient medium density to match our measured shock velocities almost exactly, as you can see in the table. And then we also match the age estimates from the optical quite well. So interestingly, this is for the case of a uniform density medium. We cannot get such a good match for a stellar wind profile or S=2 case. Okay, so I'll just put my conclusions up there and I'll be happy to take any questions. Thank you.
We have time for a very quick question. Seeing none, let's thank Paul again. So our next talk is also a lightning talk. Is Dennis Leahy, Supernova Remnants in the Small Magellanic Cloud. Dennis, this is 5 minutes long. Whenever you are ready.
Okay, just a second here. Okay, so this is work I did last year in collaboration with Miroslav Filipovic at University of Western Sydney. So it's a study of the properties of the SMC supernova remnants using simple spherically symmetric models. The idea, anyways, I don't have time to review supernova remnant evolution. There's so much work, including new work at this conference. So I've only collected a sample. The important ones for the work here are the self-similar solution of Chevalier and the unified solution of Truelove and McKee. So the basic idea, here's an image from Gilles Ferrand's 2020 paper showing a simulation in 3D with 1D initial conditions and 3D initial conditions to try to give an idea of the asymmetries. We ignore the asymmetries and assume spherical symmetry. Here's the initial conditions for the self-similar evolution from Chevalier. I put that into the Pluto hydrodynamic code and evolved several models over a range of time scales of 10 to the 7th and a range of radii of 10 to the 7th, so roughly 10 to the -5 to 100 parsecs. And this is the output of the code. But before going over this, I want to go back to Truelove and McKee and mention there's the unified evolution, which is different self-similar. So self-similar, you have a single function which applies for all time and scales with radius and time. That's the Setov solution. For the unified evolution, you have a different function for every time step, but they still scale with the initial conditions. So I've defined dimensionless values for the observable quantities, the emission measures and the emission measure weighted forward shock temperature, and plot these from the simulations here and put that into a code, which is the Python code, which also includes electron-ion equilibration, and then apply that to the set of 20 supernova remnants in the SMC. The results are over here. So this is with the 3 inputs of the shock radius, the shock temperature, and the shock emission measure, you can get out the age, the explosion energy, and the density for each remnant. So the ages roughly follow a linear relation that so it's consistent with a constant birth rate up to the point where your sample gets incomplete. Both the densities and the energies follow log normal distributions, which is consistent with what I found earlier for Milky Way supernova remnants and for large Magellanic Clouds supernova remnants. Here I just summarize all the samples, 20 in the SMC, 50 in the LMC, and 2 different subsets of galactic remnants in different longitude ranges, and the derived birth rates, energies, and densities, and they're in a log normal or dispersions as well. So now there is interesting result here. The SMC has a very high birth rate for its mass, and that may not be unexpected because it's known there's been a recent burst of massive star formation in the SMC. But the thing I find a bit surprising is the mean energy is much higher than the Milky Way or LMC remnants, but that could be caused by low metallicity. And here's a recent paper on supernova explosion calculations based on metallicity. This is the compactness parameter. So basically, low mass progenitors are on this side and high mass progenitors. But for the low mass progenitors, the low metallicity explosions are about 20 to 30% more energetic, which doesn't quite match this factor of 3 that we're finding. Okay, I'll end there. My time is up. Thank you.
Thank you, Dennis. Do we have any questions for Dennis? I'll ask a very quick one. You haven't, this is for the SMC, but I imagine you did the same analysis for the Milky Way and the LMC, and that's how you got the numbers to your table?
Yes, that's right. These are from, this is early, the SMC is the most recent.
Okay, there it is. I see the notes now.
Yeah.
Okay, let's
Okay.
thank our speaker again. Okay, so next we're going to go with Brian Williams from Goddard. Brian's going to be telling us about all of the amazing things that we're going to be able to do with Prism in the future. Brian, this is a 15-minute talk.
Okay, great. Let me share. And Dan, just confirm that you can see this and hear me.
See it.
Okay, great. Well, thank you for having me here. I'm really sorry I can't be there in person. I would have loved to see you all, but I am going to tell you about some of the science specific to supernova remnants that we can do with CRISM. And so I think a lot of you know this, but just as a reminder, what is CRISM? Well, the name of the game here is high resolution X-ray spectroscopy. So this is at the top left, you can see a very famous image from Chandra of Kepler. So Chandra, of course, is famous for high resolution imaging, moderate resolution spectroscopy, as you can see in the top right. With CRISM, we're sort of going to the opposite end of the parameter space. We're not going to have super high resolution imaging, but we are, of course, going to have very high resolution spectroscopy. So you might take a spectrum like this in the top right from Chandra and turn it into something like this that you'll see with CRISM. So we'll have about 2 orders of magnitude better spectral resolution. And I'll do that one more time just for effect. So this is actual data from Chandra in the top right. And of course, this is a simulation of what we might see from CRISM when we get on orbit. So just a quick summary slide of what we are. We are a JAXA-NASA collaborative mission. We have ESA participation on this mission as well. We have 2 instruments. This is down from the 4 instruments that we had on the predecessor mission to this, which was Hitomi. But the 2 instruments that we have are Resolve and Extend. Resolve is the main workhorse instrument, of course. This is the soft X-ray spectrometer. This will provide non-dispersive high-resolution X-ray spectroscopy over the soft X-ray band from about 0.3 to 12 keV. Extend will be a very wide field of view, about 40 arc minutes on a side, soft X-ray imager that'll have CCD resolution for the spectrum. We anticipate launching in less than a year in spring of 2023. Of course, the mission is designed to recover the science that was lost with the demise of the Astro H/Hitomi mission in 2016. So speaking of Hitomi, of course, I think everyone knows that we launched in 2016. It was working very well prior to about a month into the mission. And then on day 38, we were lost due to an operations mishap. We had even been exceeding requirements. Even with only a few weeks of observations and us not being even fully turned on or calibrated or anything like that, we observed about a half a dozen science targets, and we currently have 13 scientific papers out on that. You can search ADS. If you go and type in Hitomi collaboration, you can find all the papers that we have. And most importantly, we got a brief glimpse into the power of high resolution X-ray spectroscopy, and I think I'll I'll be able to convince you in this talk, if you're not already, that this is truly a transformational leap forward in what we can do in this area of parameter space, which has not been very widely explored yet. So just to show you that we really can do this, this is a picture on the left of launch in 2016. I don't have time to get into the details in this talk of how we do this, but we have to be very cold to do this sort of spectroscopy. So we have to cool our detector down to 50 millikelvin. This is an actual plot on the right. So you can see on the left, we launched on February 17th. And if you look at the plot on the right, you can see this is a plot from February 22nd. So about 5 days after launch is when we turned on the cooling system to cool the detector down to 50 millikelvin. And we really can do this in space. We've cooled the detector down. And in fact, you can't even see on the scale of this plot the jitter and the cooling on this. So it really is 50 millikelvin plus or minus a very, very small number. So what can we do with this? This is a real spectrum. This is from Hitomi. This is the Perseus cluster. We observed this for about 200 or 250 kiloseconds or so. What you mainly see here, the first thing that should jump out is the 6.5 keV iron K alpha line that we of course see in ubiquitous across the universe. And so, you know, that's obviously the broadest thing here. What I would point out is that we don't actually die off below 3 keV like it looks like. Again, we weren't actually fully turned on at this point. So we actually have response going all the way down to about 0.3, but we had a filter, a huge blocking filter that was cutting off all of our response below 3 keV that we had not even taken off yet. Because again, we were just in the commissioning phase with Hitomi of turning this thing on. So if we zoom in on the iron K alpha feature here, this is what happens when you give this to the public outreach folks and they make a nice artist conceived image here. So we have the real data here in white, and the red dashed spectrum there is the previous best spectrum that we ever had from the Perseus cluster, and that's from Suzaku. So of course with Suzaku, you can see the iron K alpha line quite clearly, but you can't really make out the various components of it. A lot of these other faint features here that we can clearly see with Hitomi were just either not identifiable at all with CCD spectra or barely identifiable. So this is really, as I said, a leap forward here. This is actually from our Nature paper in 2016, where we zoom in on the iron K alpha line. And of course, why am I presenting cluster spectra at an SNR conference? Well, it's because I'm trying to demonstrate the power of high resolution spectroscopy. If we can do it for a cluster, we can do it for a remnant as well. So this is the iron K alpha line. We have about 21,000 counts just in this line, just from that one pointing from Hitomi. We see again that the blue line here represents the CCD spectrum from Suzaku. The black data points and the red line going through them are the actual data that we got on orbit from Hitomi. So we really were not only resolving the various components of this line, you can see there are 4 components to this, but we were actually resolving the width of these lines here. And we got a turbulent velocity of about 165 kilometers per second from this. So we do have imaging capabilities as well. We're obviously not a high resolution imager, but we do have some. And in fact, if you take the resolve field of view, or as it was called at that point, SXS, and put it on the Perseus cluster, you can actually make a rudimentary image of the blue shifted and red shifted emission just from the iron K alpha. And you can sort of see the 3D sloshing of gas that's happening on this massive time scale. And again, if we can do this for one extended source, we can do this for any extended source. So we think this is a powerful instrument that will be useful for supernova remnants. The real thing that an instrument like this is built for is for doing high resolution spectroscopy of extended sources, so like clusters or like supernova remnants. I'll show you a few hardware pictures here. This is the detector that we have. You can actually see it there, held in someone's hands. It's smaller than a postage stamp, a few millimeters on a side. This entire thing was built at Goddard and was delivered just before COVID hit, delivered in November of 2019 to JAXA. This is a picture of the entire dewar. This is ballpark a meter across or so. And most of what you see here is all part of the cryogen system to keep the entire thing cold. So again, the picture I just showed, you're talking about a few millimeters across down in that barrel that's looking down there. And this entire thing is built to keep the entire system cold. Here are a few technicians working on the dewar. There's the dewar undergoing some further testing. And again, this dewar is, 4 or 5 feet tall, 3 feet or so across. But this image, this is from just about a month ago, and this is actually public. You can go to nasa.gov/CRISM if you want to see this pic in full resolution. I highly recommend you do it. I don't know if you all can see my mouse. If you can, that's fine. If not, that's okay. But in this little window here, this is in-flight configuration. The dewar that you see is actually in the spacecraft now. So it has been fully installed. It's not coming back out unless something goes wrong. But this is in there. The entire spacecraft is sitting in a high bay here in Scuba Space Center. It's about 5.6 meters high. The mirror assemblies have been delivered to Japan as well. They were just delivered. The last one was delivered, I think, in June or July. So basically all the hardware is there. And in fact, this is a picture just from about a week ago. This is us going into the giant thermal vacuum chamber. Our spacecraft is 5.6 meters high, so you can sort of ballpark how big that vacuum chamber is. It's comparable to the vacuum chamber at Johnson Space Center that Webb was tested in. So the door in this chamber closed just after this picture was taken. We'll be in there for about a month, roughly the month of August. We'll come out of there in early September. We'll put the mirrors on and we'll resume further testing, and we will ship to the launch site if everything goes well in early 2023. So on to some SNR science. I thought it would be fun to go back to some of the stuff that we did with Hitomi. So we heard an earlier talk in this session from Paul about N132D. This is a very bright X-ray remnant in the LMC. As Paul said, it's a few thousand years old. This was one of the targets that was observed with Hitomi while it was just in the commissioning phase. And this was nowhere near a full observation. It was only, I think there were only a few hundred seconds or maybe a few kiloseconds of useful data on this. We were not calibrated yet. But that is the iron K alpha line there on the left and the sulfur line at 2.4 keV on the right. And from this, we were able to get that the iron line has a bulk velocity that is different than the sulfur line. So we have a paper, you can look it up on ADS. But basically, we determined that the iron K alpha emission has a bulk velocity of about 800 kilometers per second with respect to the sulfur line. So we think that we're actually seeing differences in the velocity of the ejecta of various elements here. Now, you can sort of mentally do the math here. If you look at the iron K alpha line there on the left, because this is done in counts, you can see there's 1 count, 2 counts, 3, 4, 5. I believe there were 17 photons in this iron K alpha line. So obviously there's a lot more that we can do. If we got a result with 17 photons, imagine what we can do with many more photons if we get an actual, real observation of a decent length. Another target that we very briefly looked at during commissioning for Hitomi was G21.5. This is a pulsar wind nebula surrounded by a supernova remnant. What was interesting here was that we saw some absorption features that we were not expecting. So if you look at the black and red lines there, you can see those absorption features. There's one at about 4.23 keV, and there's another one that's about 9.3 keV. And we were not expecting those. And perhaps they were just calibration uncertainties that we hadn't figured out yet. But the blue line is observations of the crab, which was also observed by Hitomi. So We did not see those absorption features in the crab. We only saw them in G21.5. So we haven't really solved this mystery. It's a, to quote an unwise man, it's an unknown unknown that is very exciting for us. Is this something that's purely a calibration feature that we just hadn't figured out yet? Or is there something interesting going on at those energies? I don't know. Here's a simulation of Tycho. This is the, if you look at the top right, you can see the resolve field of view. We're 3 by 3 arc minutes on a side. So Tycho's about 8 arc minutes across. So we can't get the entire remnant in one field of view, but we can get a pretty good chunk of it all at once. And I did the simulation, and I did it as best as possible to encapsulate, you know, the broadening of the lines due to both thermal, you know, just the hot gas that's thermally broadening the lines, and the Doppler blue shifting and red shifting that we might expect to see at that position. So this is something that as we look at various remnants, you know, we'll be able to do line diagnostics just purely from either Doppler expansion or thermal expansion or both, that we have not been able to do before. So if you want to know more about the science we can do with this mission, I encourage you to look at our white paper that we published. It's on ADS, it's on archive. It's under the author Chrism science team. We have just about everything there. We even talk about exoplanets in this, but we really covered briefly every area of science that we think we can do with this mission. So where exactly are we on the mission timeline? I covered a lot of this. We are looking at a launch in spring of 2023, so less than a year from now. We are looking at start of AO1 observations in late 2023 or perhaps early 2024, depending on when we exactly launch. The first 6 months of observations are classified as performance verification targets. Those are for a while proprietary to the Chrism science team, although they will become public after a year. And I have put up here just a screenshot, and this is public. It's been public for more than a year. This is a screenshot of the targets that we will be observing that are relevant to supernova remnants as part of the performance verification phase. So you can see some of your favorites here. We have SN 1006. We'll be pointing at SN 87A, Cygnus Loop, Tycho, W49b, and CAS-A. And then we have the same definition for priority A and priority C that you're used to. Priority A are targets that are definitely going to be observed as part of the PV phase. Priority C are targets that if we can get to them, we will observe them. So for instance, Kepler is one of those, RCW 86. If we have time to observe those in the PV phase window, we will. If we don't, then they just won't be observed. So one of the questions that I get a lot is, oh, you put out the PV target list, but you didn't include my favorite object. Well, I have good news for you, because if we didn't include your favorite target in the PV phase, you can propose for it in the general observer phase, because after we leave PV phase, we are entirely in geo phase for the rest of the mission. And we have funding for this. I'll talk about that on the next slide. But if there's a target that you want to observe, you know, once we hit launch plus 9 months or so, we are entirely in the geo phase, and we will run just like Chandra, Hubble, XMM, whatever. We'll have a yearly call for proposals. We have a pretty generous funding opportunity for this if you're in the US.
Excuse me, 1 minute,
yeah.
please.
Perfect, I'm almost done.
Thanks.
So with that said, the geo phase program is, we have about $6.5 million or so to cover every cycle for that. We have funding included for lab astro investigations. If you do laboratory astrophysics, please do propose for that. We have resources such as a help desk. We have proposal tools, response matrices. Everything is on our website that you can find. And with that, I'll put up my closing thoughts that high resolution X-ray spectroscopy is a largely unexplored space. I hope I've given you a brief glimpse within this 12 minutes of what we can do with this. And I will close by saying that I believe CRISM will be a pioneering mission in much the way that OSCA was a pioneering mission for Chandra and XMM in the way that it flew the first CCD imagers. So I think if we're going to fly missions in the future, such as Athena, we will have to have missions like CRISM that go along and show us, what the high resolution X-ray spectroscopy field can do. So with that, I will end. I'm happy to take any questions.
We have any questions for Brian? Wolfgang.
First of all,
yeah, go ahead.
first of all, Brian, I'm very disappointed that you're not even taking the time to remove the PITCMU colloquium March 2022 on your lower right-hand slide. Very disappointed.
Sorry about that. Of course, I thought I
You have questions about the Perseus cluster. I find the RNK alpha line, I don't know much about the atomic physics there. So what are the different components? You go back to the Perseus cluster.
It's right there in front of us.
Oh, yeah, sorry, it's okay. What are the different components there? Where do they physically go?
Sorry. Okay, I didn't hear the first part, but I think I heard the bulk of the question. What are the different components of this iron line?
Yeah,
Is that-
yeah, ultimately, I mean, it's not like the Bama series, it's like the Lyman series for hydrogen, right? No?
Yeah, so I'm sure there's someone there who's better at at atomic spectroscopy than I am, but as I understand it, these are the different components, the components of the iron K alpha line. So you have like the forbidden resonance. I forget there's an I in there somewhere, intercombination or something like that. But yeah, these are basically all the different components of a single line. And I think if you go to that paper, you'll see them. But yeah, basically, so with Perseus, we had the benefit of the line width here, as you see in that feature, is only about 165 kilometers per second. So we were actually able to resolve these individual components of a single line. Now with supernova remnants, we will be able to do this. Well, it's not as, maybe not, just because of the nature of the objects, that they expand at thousands of kilometers per second. So these may get more blended than they would be in a galaxy cluster. But there's certainly going to be objects out there where we'll be able to identify the individual features that make up a single, what we think of as a single emission line.
We have time for one more question, and I'm gonna go ahead.
I was curious to know what the spec resolution of CRISM is compared to Hitomi. Is it better? Is it the same?
By definition, we're drawing it up to be exactly the same. So our requirement is less than 7 EV, and that's a constant 7 EV. So that's one difference between us and a dispersive spectrometer, because with a dispersive grating, it can vary with wavelength. So, but with a non-dispersive spectrometer like what we have on CRISM, it's constant in energy. So our requirement is 7 EV or better. What we measured with Hitomi on flight was 5 EV. And so I can't guarantee you it'll be 5 EV, but that is our goal, to be certainly less than 7, and we hope more like 5 EV across the entire spectrum.
Okay, thank you.
Let's thank Brian again. Okay, I would like to welcome Dan Milosavljevic, who's going to wrap us up. He promised he had 67 slides. I also threatened him that if he went through all of those.
You got it, Dan. You have a train to meet.
Don't worry about it.
No,
Okay.
no, I'll aim for 10 minutes. I think everybody is
Aim
ready
for
to stand
20.
up. Aim for
So,
Do you want the microphone?
I think as long as people can hear me, I think I'll be fine. I'll take that off. It's really a pleasure. It's also humbling, and I take this responsibility seriously, but there's no way that I can mention everybody in every reasonable capacity. What I'm showing here is things that stuck out to me and areas where I think there are real development to be had in the field overall. I click same thing, everybody. There we go. So first of all, why are we here? And so to discuss more about the connections to be made between supernovae and supernova remnants, and as addressed here in this workshop, connection to the progenitor. Because as we move forward and try to understand how supernovae explode and evolve into remnants, increasingly we understand that having true constraints, true understanding of what the progenitor system is vital towards that. And in order to do that, we need a balance of information that comes from supernova remnants and supernovae. Supernova remnants enable detailed observations, as I'll go into in a little bit. But of course, we'd only, there's only so many supernova remnants that we can do in this rich detail, and supernova studies provide kind of statistical information and peak energies and velocities, etc. Along with distinct layers. And I highlight here work done by Roger Chevalier. It's this list that I come back to routinely. There's many talks that highlighted on this, and we'll return to this in many ways. I'm drawing up here the supernova remnant connection game. Jaco spoke about this already today. You know, we have a spectroscopic classification that's largely based on optical spectroscopy with a little bit of light curve. We talked about different metrics, the iron K line. I'm going to point here in particular, the best way, the most consistent manner is using light echo spectroscopy. And we're able to do that for Cas-A and Tycho. Then it gets a little bit more complex as far as with the other remnants. And now using X-ray abundances is often the strongest way to do this for some. We had talks today about different methods in making connections. If I go forward, we would love to have a light echo to understand the crab. I didn't point it towards exactly a type 2 or type 2N so that people don't get upset with me. Okay. And then W49B originally is a 1A because of iron abundance, and then Laura Lopez and others thought, hey, maybe it has some jet-driven activity that enhanced the iron production and put it back on the 1C broadline. But then we talked today how with Vikram about how it may be more of a 1A. RCW86, Jaco, I mentioned this yesterday. So one of your favorites of the past. I did find the paper, so claiming it to be a calcium-rich transient explosion. Okay. It's in nature, so it must be true, okay? Which is to say they found a surviving companion and they claimed that it was enhanced with calcium. It was polluted by the explosion, okay? I'll talk about that. I see Wolfgang's eyebrows go up. So anyway, it's the connection game. It's a shell game. Can you follow it as we move around the board, right? Okay, and then this one's always fun for me, Kepler. So I put it in the middle because it often gets mistaken for a core collapse explosion. In fact, I was at Caltech on a talk on gravitational wave explosions, and there it is, given as a prototypical asymmetric core collapse supernova. And so, yeah, we talked about these things. Okay, speaking more about why we study remnants. There's a lot. It is often the case that because there's transients have new events coming around routinely, they get a little bit more exposure. So, here's a press release for a study of supernova 2011 BH. But of course, this is a fantasy, right? What really 2011 DH was a point source, okay? Don't be distracted by the beautiful host galaxy, right? It's just a point source, okay? And then this one came out in 2010 for 2010 JL. This is fantasy, right? Some artist conception. It really is just a boring dot in the sky. That changes with remnants. Wow, okay? Here is reality. Yeah, I can map out the material. I can follow it over many years, as we'll discuss in a little bit. I can see where chemically distinct areas are. I can find where asymmetries are. There are caveats to this, of course, interaction with the environment, all things that we've gone into in great detail. Okay? I'm borrowing here a quotation from Jaakko. It's an embarrassment of richness, right? So you're almost in the other extreme now, where you have so many details to which it can be complex to accommodate them all. Okay? And yet, these are not details that we should run away from. They must be confronted with and dealt with. Okay, a little bit of fun, historical fun. I thought, what were the first attempts to link supernovae with their progenitors? So Tycho Brahe, as the Danes tell me to pronounce it, or Tycho, observing 1572, and the etching I'm sure everybody's familiar with. I've noted down what he wrote in his book describing it. He was a real showman. So let's see, blah, 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 blah. Let's see. And he says here, yeah, and since I had almost from boyhood known all the stars of the heavens perfectly. So of course, he knew where all the stars are. There is a new star in its place, a miracle indeed. So it was either the greatest of all that occurred in the whole range of nature since the beginning of the world, or one certainly to be classed with those attested by the holy oracles and staying of the sun in its course and answer the prayers of Joshua and the darkening of the sun's face at the time of crucifixion. So either the most important thing or the second most important thing that's ever happened for us. Okay, Kepler was a little bit more modest. The star significance is a difficult matter to establish. We can be sure of only one thing. It's either, it either signifies nothing at all for mankind, or it signifies something of such exalted importance that it is beyond the grasp and understanding of any person. Very good. And then this is fun too. So now let's go back, because Cassé got a lot of attention today. Let's go back to the original papers of trying to understand what it is. So this is the follow-up paper of Walter Baade and Rudolf Minkowski. And these are the incredible observers of the past. Okay, I routinely go back to Minkowski's papers on Cassé, and he has these numbers. I have no idea how he came up with them, but they're always good, right? They always worked out to be correct. And Walter Baade, long history there. Anyhow, so this is the paper Optical Follow-Up of Radio Sources. Okay, Cassé, a brightest radio source in Cassiopeia. So they describe it as broken bits of nebulosity of a most remarkable kind. And here's the field of view. You can see it doesn't look very exciting in their photographic plate. And Rob, if you're on the line, I borrowed one of your recent MDM images of Cassé to overlay to see. So ghostly in the back is what we see today and where everything is. And this is what they were going by. Okay. Courtesy of Rob Beeson. And here's the spectroscopy. They noticed material moving at thousands of kilometers per second. That's on the top. That's ejecta. This is QSF. This is the circumstellar material. Anyhow, they didn't have much to say of what it is, but they had very much to say of what it isn't. Okay, so I'm highlighting up here. This is it's obviously small compared to random motion. This is quite different from the conditions found in shells of novae and supernovae, and clearly shows that the nebulosity is not a shell of this type. Okay? So, but they couldn't leave it at that. You see the footnote on the bottom here. Okay? They went further. Since there is every reason to believe that Cassiopeia source has nothing to do with supernovae, the attempt by Shklovsky to identify the source with a new star of 8369 is beside the point. Right? It means that it's irrelevant. Okay, talking about during this meeting, I've noticed many beautiful animated GIFs. We've been following these remnants for a long time. In fact, the age of our research is now approaching meaningful timescales of supernova remnants, right? Where we can follow the ejecta moving along with the shocks. And there are a number of talks that show these GIFs. I loved your quotation, all these, the songs that you can listen to again and again. So these are the remnants that you can go back to that you always enjoy. Okay, also going back to the X-ray. Not only is it a testament of our research staying the course, but also the longevity of space facilities. So Chandra being operational for so long, being able to return to the remnant and follow its evolution over many years. Okay. I'm starting to sound like Rafaela, whose talk was most like a proposal, trying to justify why I need to return to these objects again and again. Okay, and I'll just have a quick plug for work done by a former grad student, now postdoc John Banovitz on EO 102. This is Hubble Space Telescope images. Again, just showcasing where we are. We can watch these ejecta expand with time. Again, HST, its longevity. These are 10 years separated, and we're able to follow the evolution of the remnants. Okay. One thing that kind of concerns me in understanding of supernova explosions is going back to the progenitors. We've been successful in the case of hydrogen-rich supernovae, okay, where we go back after the scene of the crime, we can find, we do a nose count, we find that there is a hydrogen-rich star beforehand. However, the problem becomes with stars that aren't hydrogen-rich. So in the case of the stripped envelope supernovae, when we go there, we don't see the stars that we had anticipated to, and it's starting to become a little bit concerning. Now, we're getting better with time, okay? In the sense of the 2B explosions, there seem to be, we can find some progenitor stars, but as you get increasingly stripped, the less likely or the absence of evidence that there is an actual, what that progenitor star was. And remember, 87A was not the red supergiant that we'd presumed it to be. It was a blue supergiant. And we've had now yellow supergiants with the type 2B explosions. So the progression, I can just move on. And also another thing, these detections at extragalactic distances. Okay? One must always be suspicious, because whenever the closer we look, so here is a pre-explosion, when you look in the field, whenever we get more sharply resolved images of these field at extragalactic distances, we see more stars start to appear. Okay? So there's been many identifications of type 2B surviving companions that are B stars, blue stars, right, in extragalactic systems. But those are those are a few pixels unresolved. The closer the look, the more stars that often pop up as a result. Okay, I'm going to highlight Wolfgang's work. So that's why a remnant can be so powerful in this sense, right? We're not talking about megaparsecs, we're talking about kiloparsecs. And we have the opportunity to do really detailed nose counts of stars. The thing that I would love to talk with people more about is what is the bona fide way to move from a candidate star to the one, right? We talk about polluting the star, but what exactly are we doing? Is there more modeling that we can do? There's certain cuts and such, but that's kind of the lacking that I see. We talked a lot about surviving companions for 1As. We talked about the lack of kind of main sequence stars, and the one that really stuck out to me was 11FE because it was so nearby. You go back to previous HST images and you don't see anything to very strong constraints. We had talks about the test light curves, which I found incredible today. So we remain, whoever watched this show, Leonard Nimoy, In Search Of, this is kind of what we're still doing these days, in search of companions. What time am I at, by the way? I want to be reasonable. Okay, I'm going to move forward, but we had Jaco showed that slide of the figure from the Schaefer and Pagnata, and then we had a great talk from Procida today, and we had other discussions about surviving companions. Okay, other things. So we are cautiously moving away from spherical cows and understanding of supernovae towards 3D with asymmetry, both in theory and observation. There's still great utility and will always be for 1D simulations and understandings, but as we see that these remnants display asymmetric features, we need to incorporate that in understanding in some way. And we had talks, again, theory and observation, so theoretical modeling in 3D and showing 3D reconstructions of remnants, and of course that has a special place in my heart. This I'm going to borrow from Abby in a discussion. So we had some notes about how measurements of chemical abundances don't match the nucleosynthesis yields. Okay, but there's two things that make this hard. One, it's challenging to make those chemical abundance models in the first place. And then yet it's also challenging to make measurements of those chemical abundances themselves. Okay, so there's like an iterative process that goes back and forth. Okay, jets. I have to say something about jets. There was a great Slack channel feed from the Soaker group about anybody that had a remnant that had some connection to jets, you could draw arrows through. And I'll mention there's other people that have played this game today. Craig, if you're online, I know you're fond of bagels and breadsticks, and you attach significance in Cas A to the parentheses, as I remember. And then the Smith paper, I remember they found importance with the neon, and they thought maybe that was a significant access. And for grins, I just wanted to remind everybody that the crab has this unusual funnel shape coming out of it, just for fun. And then I'm going to throw my own kind of log into the fire here. One thing that's always fascinated me with 87A, if you look back, the speckle interferometry that they did of that source, right, at the time of it is exploding, months after exploding. So this is like very early in the evolution of the supernova. They notice an ellipticity, and this is north up, east that way. If I flip it the other way and I overlay it with where we have the ejecta direction, it's in the same orientation, right? So that asymmetry was very strong at the earliest stages, and it's retained itself throughout the evolution. Anyway. Oh, and I just found it funny that they used a VCR to do that recording of the speckle interferometry. Finally, yes, as we move towards understanding in 3 dimensions, we can make connections between the simulations and the observations. This is something, Abby's work and Michael's work that kind of really excites me. We're now getting at stages where we're able to do that, right? And provide, things to match. So Abby was emphasizing the power spectrum of features. So we can identify, I'll never forget one of the first talks that I gave about the rings in Cas A. Somebody says, has nothing to do with the explosion. That's purely an influence of the surrounding environment, right? We actually have ways that we can test that now, okay? And demonstrate where they're originating from. Michael was able to go in the VR. If anybody wanted to do afterwards, maybe we can find time. And then I also want to I never got a chance to show this because of the pandemic. Muse got a lot of attention during SOC, as it should. But there's also a wonderful, amazing instrument on CFHT, CTEL. So this has an 11 arc minute by 11 arc minute field of view. Over 1 million spectra went into this creation of a 3-dimensional reconstruction of the Crab Nebula. And this is not a simulation. This is what the Crab Nebula looks like in 3 dimensions, at least in H alpha and nitrogen. And our own work is we have new cubes now at other emission lines, and we're going to hopefully be able to do a chemical abundance map of the crab. And also an artist reached out to us who does these 3D sculptures. You can order this online. You can have the crab on your desk if you want in 3D. Okay. In the interest of time, I'm going to move forward. One of the things that really plagued me is that, not only is where the ejecta, but how much is there. And we have these abundance yields that, to me, often show that most of the, nickel and what we would see as iron today are still at low velocities. And yet, for instance, in Cas A, it's above 3,000 kilometers per second or 4,000 kilometers per second. Discussion of this has moved us to understand that the progenitor star, we had talks about this, really influences the mixing and how far out it can go. Okay. Finally, another meme. So the differences between Hubble and Jwc. The hope is that Webb, being sensitive to the mid-infrared, will be able to help us understand this. Okay. And it was mentioned, I'm a PI of a program with have a wonderful team of people behind us. We have an extensive observation strategy for Cas A. Data just started coming in last week. I'm very excited to be able to share that soon. If you come with me afterwards and we get a beer, maybe I can show you some early data as well. And we have a lot of great science that we can potentially do. And I'm just going to skip over that in the interest of time. Final thought, okay? As a remnant community, we got to get better at finding more remnants. We can't, but I'm just saying that sarcastically. LSST is coming online soon. And the claim is that they'll be able to find, 1 million supernovae per year, potentially. You can always counter, well, the majority of those are going to be crappy light curves to begin with. What kind of science can you do, right? But still, there is going to be an explosion of activity. Like here's the plot. This is number of supernovae discovered each year. It starts around 96. You can see it around 100. And previous to this, since the beginning, since days this week and beyond, let's say there's a couple hundred. So cumulatively, there'll be of order 100,000 supernovae discovered up until LSST, and in the first year, discovering, let's say, of order 1 million. And that's a huge explosion. There's going to be a lot of activity. And all of a sudden, it will enable statistical studies, diversity studies, but to have confidence in the explosion physics that people are doing into these, integrated point sources, they need to fall back on what we can do as a remnant community. Okay, finally, it's been so wonderful to meet here in person. I wish we had a way to interact more with the virtual participants. Slack was a great medium for that. There, in other communities, there can be a little bit of a competition, and I use this phrase recruiting from the human race all the time, but not here. Okay, this has been a wonderful meeting and setting, and I give all the credit to the organizers and the people that are here for maintaining a very warm, inclusive, inviting atmosphere. It makes for better science, in my opinion, and I'm really grateful for the opportunity to speak here amongst everybody. Thank you.
Okay, that actually closes the workshop. Thanks, Dan. I would like to say before we wrap things up, thanks to Rudy and
Yes.
and the director's office for accepting this as a workshop, and the members of SOC for putting together a fantastic program. So thank you, everybody.
And thank you.
And I apologize. I'm